Right, here's a new video of forces questions. We're starting with a lift here. I mean, this looks like something out of a disaster movie, but I assume it's not quite as grim as it looks. A lift has a mass of 500 kilograms. Right, I haven't put that on here. There's a lot of stuff that we don't have on here. So we've got 500 G going down. That's just for the lift. Designed to carry a maximum of 8 people with a total mass of 560. So we've got another 560 G possibly on top of that. The lift is supported by a steel cable of cross-sectional area 3.8 times 10 to the minus 4 meters squared. When the lift is at ground floor level, the cable is at its maximum length of 140 meters. Mass per unit length of the cable is 3 kilograms per meter. Show that the mass of the cable is 420 kilograms. Right, well, that's going to be 3 times 140. 3 times 140 equals 420. Right, there's not much to do with that. The lift with its 8 passengers is stationary at the ground floor level. The initial upward acceleration of the lift and the cable is 1.8 meters per second squared. Show that the maximum tension in the cable at point P is that. Right, so this is a maximum because when we start winding the cable, we're going to get less mass in that. So the total force going downwards is when we need another 420 G. So we've got all of this added up in order to have the downwards force. So we've got F equals ma is what we're going to do on this. So we've got T, which is going up. T minus all of the weight is the mass times the acceleration. So we've got that T is going to be equal to how many G's have we got here? 500, 1,060, 1480 G plus our total mass on all of this, which is going to be that without the G, multiplied by the acceleration. So 1480, what was our acceleration? 1.8 times 1.8. So just sticking that into the calculator, we've got 1480 times 9.81 plus 1480 times 1.8. I mean, I suppose you could have factorized that, typing it all in if you'd wished. And that gives us 17183, which is 1.7 times 10 to the 4. 1.7 times 10 to the 4 newtons. Right, so that's good. Calculate the maximum stress in the cable. So stress is force over area. So we need to take that force that we've just worked out, so 17182.8, divided by the cross-sectional area of the cable. Oh, there we go. They've actually given us the cross-section. So 3.8 times 10 to the minus 4. So yeah, we just need to divide this by 3.8, and then so we've got a 4.5 times 10 to the 3, and then another 4. So 4.5 times 10 to the 7 pascals. There you go. So that's quite nice. Next, we've got all right, we're back onto newtons here, defining what a newton is. So a newton, 1 newton, is the force required to accelerate a 1 kilogram mass at 1 meter per second squared. So that's what we're looking for there. State why the equation F equals ma cannot be applied to particles traveling at speeds very close to the speed of light. Again, we haven't really done much on this yet, but mass increases with velocity or with speed, whichever way you want to go. But it's only significant when, I don't know, v is, some fraction, maybe greater than or equal to 1/100th of the speed of light, something like that. So yeah, don't worry about that one too much at the moment if you haven't got onto the later videos, and we're just sticking in classical mechanics because of course we're getting into modern physics with that sort of thing. But yeah, eventually this is why you can't have objects with mass traveling at the speed of light. They can never quite get there. You can't give them enough energy in order to get them there because the mass just keeps on increasing all the time. Right, in C, we've got figure 3.1 shows the horizontal forces acting on a car, mass 900 kilograms, so they haven't got that on there, traveling at a particular velocity on a level road. The total forward force is that, yep, and drag is that. Calculate the acceleration on the car. So F equals ma, again, so we've got 200 minus 80 equals 900 times A, so 120 divided by 900, get rid of those, equals A. So this isn't much of an acceleration we've got going on here. And we could take 3's out of this, so 4 over 30. So 2 over 15. I mean, it's really dropping down now. That's our acceleration is 2/15. So let's just get that as a, just double check on all of this. So we've got a 0.13 meters per second squared as our acceleration, 2/15. So yeah, nice. Explain why we cannot use the equation v equals u plus at to predict the velocity of the car at a later time, even when the forward force is constant. Okay, because the drag will change. Drag will change with velocity. They did say we had drag here, didn't they? Air resistance drag will change, i.e. increase with velocity as the velocity increases. Right, so that's covered the bit with the car. Now we've got some woman here in a precarious situation on a rope. She's been tied to this rope and lifted upwards. The mass of the person is 72 kilograms, so we've got 72 g going downwards. The upwards vertical acceleration is 1.4 meters per second squared. Calculate the tension in the rope. So we've got the same, this is the same question. T minus 72g equals 72 times 1.4. So T is equal to, so we've got 72 times 1.4 plus 72 times 9.81, which gives 807 newtons, which equals, yeah, we've got two sig figs everywhere, so 810 newtons to two significant figures. So yeah, weird, they've given us the same question twice essentially there. We've done exactly the same thing in each occasion, but you know, that's fine, just more marks for us. Right, onwards we go. We've now got to, we start with another definition. We've got to define the torque of a couple. So that is the magnitude of one of the forces multiplied by the perpendicular distance between the two forces in the couple. So just turn that into a sentence. Explain why the moment of a force and the torque of a couple have the same unit, Newton times meters. Well, both of us, so a moment is moment about a point. That's what we've always got with a moment. It's always a moment about a point. That is the force times the perpendicular distance from that point. So both of these involve a force multiplied by a distance. So we've already defined the torque in the first one, torque of a couple in the first one. So if you define what a moment is and then say both of them involve force times distance, then we've got that unit of Newton meters. That's the first two bits done. Figure 4.1 shows an irregular shaped metal plate of constant thickness that can swing freely about point P. Okay, the weight of the plate is 6 newtons, which they've marked on. Plate is in a position as shown in figure 4.1. Calculate the clockwise moment of the plate about an axis through the point P. So yeah, once again, we need that through the point P business. So yeah, we've got the force multiplied by the perpendicular distance. So we take the force back, and there's our perpendicular distance, is to 0.4. So we want to do 6 times 0.4, which is 2.4 Newton meters. Right, so that's that bit. Explain why the moment of the weight reduces to 0 when the plate reaches the bottom of the swing. Well, the perpendicular distance is equal to 0 because it's directly below. We're going to have the force down here at that particular point. So yeah, we're saying the force is directly below P, directly below P. Describe an experiment to determine the center of gravity of the metal plate shown in figure 4.1. Okay, so we need to say what we're doing and what we're making the measurements with. So we can hang the, so yeah, first of all, hang the shape, the plate, that's what they called it, by a point. Any point, doesn't really matter which one it is. Hang the plate by a point. 2, draw a vertical line through that point. So draw a vertical line on the plate through point. So on the plate through that point. So we'll say using a plumb line. Then we can say 3, repeat for a second point, and then you can say where the lines cross is the center of gravity. So center of gravity where lines cross. So whenever you get stuck on these and feel as though you're not saying enough stuff, always put in a bit of equipment that you're using to do a measurement or a particular task or something like that. There's always an option there. People have a tendency to forget those ones. Right, I've filled up a lot of the screen already. I'll switch over to blue for the last part. Figure 4.2 shows a section of a human forearm. Yeah, they like all of this in equilibrium. We had this earlier with different numbers. The weight of the object is 60 newtons. They've done that. The 32's there. 18's there, 14's there, 3.5's there, so it's all there. By taking moments about the elbow, determine the magnitude of the force F provided by the bicep. Okay, so right, let's squeeze this maybe up here. I've nearly run out of space. So if it's in equilibrium, we are going to have 3.5, so 7 over 2F. That's our anti-clockwise moments, has got to be equal to 14 times 18 plus 60 times 32. So 32 multiplied by 60. Okay, there's quite a lot. Yeah, well, I can't really be bothered to simplify any of that. I think with a number of numbers, I'm just going to type it in. It's going to be quicker. 14 times 18 plus 32 times 60 is 2172. Divided by 3.5. Gives us 620.6. We're all in 2 sig figs here, so we'll say 620 newtons to 2 significant figures. So yeah, relatively straightforward. They love arms for some reason when it comes to moments, but there you go. And next up, we've got what looks going to be, this looks like a standard forces resolving question. 20 Newton force acting at that angle. That's all in the picture. Determine the horizontal and vertical components of this force. So horizontal, vertical, so we're going to have 20 cos 38 degrees and 20 sine 38 degrees. Okay, let's put those in. 20 times sine 38 is 12.3 newtons. And then we got 20 times cos 38 is 15.8. 15.8 newtons. So nothing very exciting there. Part B, we've got metal block held in equilibrium with 2 wires. 20 Newton tension in each wire. Show that the weight of the metal block is about 25 newtons. Right, so the weight, if it's in equilibrium, the weight is going to be 2 lots of 20 sine 38. 20 times sine, oh, I've missed out the 20 bit. 2 lots of sine 38 times 20, so it's going to be about double what we had here. which is 24.6 newtons. So yeah, that's about 25. So that's fine. The metal block has volume of that. Calculate the density of the metal. So density is mass over volume. So they've given us the volume, and we now know, well, we need to divide the weight by G. So we're going to have 25 divided by the volume, 10 to the minus 4, and we've also got divided by G as well. So we've got 24.6, go back to 24.6, divided by 2.9, divided by 9.81, gives us, so yeah, I used the 24.6 there, so we've got 0.86, so 8.6 times 10 to the 3 kilograms per meter cubed. So yeah, that was pretty standard resolving forces and density question. It's the last one in this set. We're starting off with the usual definitions. I mean, we should be used to these by now. What is meant by the centre of gravity of the object of an object? It's the point at which the weight of an object appears to act. Define the moment of a force. The moment of a force about a point is the force multiplied by the perpendicular distance from that point. So I won't bother writing those out. We've done that a few times already. You should be getting slick on those. We've now got this toy setup going on here. Have we got anything in this description that isn't in the picture? It doesn't look as though we are going to have anything there. No, it's just saying it is the picture, right? So let's ignore all that. State two conditions necessary for the rod. Two conditions necessary for the rod to be in equilibrium. Again, the usual one: net force is 0, net moment is 0. Now we're on to the calculations. By taking moments about A, determine the distance x. So moments about A, so that's ignoring then the bit in the string, which is fine. The weight of the rod is negligible, so we've already ignored that bit. We've just got these two shapes here. So we need that 0.12 multiplied by x is going to be equal to 0.35 multiplied by 0.5 minus x, and we just need to solve this for x. So let's get rid of these, multiply both sides by 100 just to get rid of that bit there. So we've got 12 plus 35x, so that's 47x equals 35 over 2, so x is going to be 35 divided by 94, which comes out as 35 divided by 94, 0.37 meters. 0.37 meters. By determining the magnitude of the tension in the string attached to A, well, we just resolve vertically. So we don't have to worry about moments. Sometimes when people get into doing moments, they get so obsessed with them they forget about the other part of equilibrium, that we can resolve this horizontally and vertically and everything's going to cancel out. You resolve vertically, well, the tension is going to have to be equal to 0.12 plus 0.35, because those are the ones going down and the tension's going up. So that is what 0.47 newtons. Yep, so that wraps up this video.